Hello guys, let's learn common industrial controllers. In this video, first I'll write and test a simple on-off controller for the water tank system which was designed in the previous videos. After that, I'll improve its performance by defining a deadband for the on-off controller, and I'll start PID controllers. Let's start the video. In the previous video, I wrote and tested this program to control the water level manually. Now I wanna control it automatically. First, let's add a selector to the control box. I'll use that to select auto and manual modes. Now let's modify the connection settings. I need two new digital inputs for the inserted selector. After that, I'll open the symbols table in SIMATIC Manager and define two tags for the two new digital inputs, I0.4 and I0.5. Now let's open the main organization block OB1 to start the programming step. Well, if you remember, this part of my program can open and close the fill valve manually. Now I want to use this part of my program only when the manual mode is selected. Note that I added this line to turn off the fill valve when I switch from the manual mode to the auto mode. Now let's write a program for the auto mode. I want to open the fill valve automatically when the desired level is greater than the current level. So I need to use a comparator instruction. Remember, the last two networks calculate the current and desired levels in integer format. So I need to use this comparator instruction. Note that these instructions compare integer numbers, these compare numbers in double integer format, and the last group compares real numbers. You can use the help window to see more details about these instructions. Now let's continue the video and write a program for the auto mode. Okay, based on the second network, if the auto mode is selected and the desired level is greater than the current level, the fill valve will be open completely. Otherwise, according to the next line, the fill valve will be closed. Now let's download and test my program. You will see my program has a problem. Well, as you can see, the manual mode is selected. Let's press the Start push button to open the fill valve. As you see, the Start push button doesn't work. Why? Pay attention to the next network. The auto mode is not selected, but this part of my program closed the fill valve after the first network. So the Start push button cannot open the fill valve. Note that I want to execute one of these two programs. To solve my problem, I can put them in two functions. Remember, I've used these two functions in the previous video. Now I want to create two functions as my manual and auto functions for the fill valve. Well, I've created these two functions, FC1 and FC2. Now let's transfer my manual and auto programs for the fill valve to these two functions. Okay, now when the auto mode is not selected, its related program inside this function won't be executed at all. Again, let's download and test my program. As you see, at this time, the manual program is working correctly. Now let's change the desired level and enable the auto mode. As you can see, the fill valve has opened automatically, and when the water level reaches the desired level, my PLC closes automatically too. It seems my program is working without any problem. Let's test it again when the discharge valve is open a little. As you can see, when the water level drops, the PLC automatically opens the fill valve. Now let me open the discharge valve completely to see the problem with my simple on-off controller. As you can see, because of these fluctuations, my program is constantly turning the fill valve on and off, which may damage the fill valve. Now let's select the manual mode and close the two valves. Okay, now let me explain the problem with my simple on-off controller inside the auto function and also how I can solve it. Well, this diagram shows the logic of my on-off controller, which is the simplest form of automatic controllers. Now, when the error is negative, in other words, when the liquid level is above the desired level, the fill valve is closed. And when the error is positive, the fill valve is opened immediately. As you saw, because of the fluctuations on the liquid level, when the water level reaches the desired level, my program starts to turn on and off the fill valve constantly. To solve this problem, practical on-off controllers usually have a deadband around a set point, like the right diagram. When the measured value lies within this deadband, the controller does nothing. For example, if the fill valve is off, I should open it when the error is larger than 10 centimeters. And when the fill valve is on, I should close it when the error is less than minus 10 centimeters. Now let's modify the program based on the right diagram and then see its performance. Alright, now let's download and test the new program. Well, let's select the auto mode. As you see, the fill valve has opened automatically to increase the water level. Now let's open the discharge valve to see the performance of my new on-off controller that has 20 centimeters as its deadband around the desired level. As you can see, my controller doesn't open and close the fill valve with a high frequency and can keep the liquid level at a specific range around the desired level. Now let me open the discharge valve completely. Okay, the new on-off controller with its deadband is working properly.
Okay, we generated a code to control the water level of this tank. In the manual mode, we could use these two push buttons to control the water level. By selecting the auto mode from the bottom selector, I could activate FC2 function to control the water level based on the on-off controller program that I had written already. Naturally, when I open the discharge valve to decrease the water level, the controller tries to keep the water level on the range of the preset desired value. Now let me explain manual and automatic controllers. According to the diagram, in a manual control system, the output of a process is controlled by its input, which is controlled by an operator. As an example, in the bottom image, notice that an operator can control the water level just by observing it from the glass window on the tank, or on the next image, an operator can control the temperature of a furnace by observing the temperature gauge to determine to increase or decrease the flow of a fuel amount into the furnace. Notice that although designing manual controllers are simple, but we have to deal with some problems in using them. As an example, in these types of control systems, we would need to use an operator to check the process parameters continuously to determine how to control the input parameters. Therefore, the final performance of a manual control system depends on a vigilance and preparation of its operator. So in general, a manual control system is an open-loop control system. It is less reliable, efficient, and accurate compared to automatic controllers. Therefore, we usually prefer to design and use an automatic control system. According to automatic control system diagram, the control system uses a feedback signal to compare the output with our desired value. This diagram is called closed loop control system, and this is its diagram with more details. Closed loop systems can automatically correct the errors occurred in output by using its feedback loop sensor. As an example, as it is illustrated on the bottom right side, the temperature of the furnace is measured by a sensor and it is fed to the controller as PV value. Or the water level of the tank is measured by a level sensor and fed to the controller. Let's assume that we wish to keep the water level of the tank at 150 centimeters. Now, let me show you how we can keep the water level inside the tank at 150 centimeters by using an automatic control level system. Let's assume that the sensor shows the current water level in the tank is 120 centimeters. Therefore, the difference between current value of the water process value and the set point is equal to 150 minus 130 equal to plus 30 centimeters. Since the amount of error is plus 30, the controller decides to open the inlet valve. Naturally, by opening the inlet valve, the water level is going to rise. It even might rise as much as 160 centimeters, which it makes the error value equal to 150 minus 160, which would be equal to minus 10. In this case, the controller might close the inlet valve or even to open the outlet valve if the control is connected to the outlet valve as well to get the water level back to 150 centimeters. This is the way that an automatic control system functions to do the controlling job. Now let's see how an on-off controller works. On-off controllers function based on the sign of error, not its amount. Anytime the amount of an error is positive, the inlet valve is open, and if the error value is negative, the inlet valve is closed. Remember that we implemented an on-off controller to control the water level in a tank. In that case, by using the PLC as an on-off controller, we noticed that anytime the water level reached the desired level and the error value equal to 0, because of some fluctuation on the water level, the PLC started turning the inlet valve on-off continuously, which increased the fluctuation. Turning an electrical device on-off continuously is very harmful and decreases its useful operation life. That is why usually we implement on-off controllers with a dead band. Therefore, the PLC didn't have to try to keep the water level at a certain level. If we wish to control the water level precisely without fluctuations, we need to use an analog inlet valve. By using an analog inlet valve, we can control the input water volume precisely, and instead of using an on-off controller, we can use a PID controller. A PID controller is consisted of three basic coefficients: proportional, integral, and derivative. First, for the sake of simplicity, let's learn how a proportional controller functions. According to the diagram, a proportional controller multiplies the error value by a coefficient number and applies it to the inlet valve. As an example, if the error value is equal to 10 units and the Kp is equal to 2, then the output of the proportional controller will be 20. For the water tank system, we can assume it is a voltage which should be applied to the inlet valve. Naturally, if there is a larger error between the water level and our desired level, the proportional controller will generate a bigger voltage to open the inlet valve as much as possible. In the same way, if the error value is minus 5 volts, then minus 5 times to 2 is equal to minus 10 volts is going to be applied to the inlet valve. Notice that we cannot apply all produced voltage by the proportional controller to an analog valve. As an example, if you remember, the voltage range of the inlet valve in factory I/O is limited to 0 and 10 volt DC. So we cannot apply 20 or minus 10 volts to the inlet valve. The performance of a proportional controller can be explained based on the below diagram. Notice that as shown on the diagram, the error amount value as the controller input is multiplied to a constant number Kp. In practice, we need to consider some limitations for the output of the proportional controller. As I mentioned earlier, in some cases we are not allowed to apply negative voltages to an electrical device. In those cases, we need to remove the negative voltages like the right diagram. In the water tank system and for the inlet valve, we also need to limit the controller's output to maximum of 10 volts. Since voltages greater than 10 volt cannot be applied to the inlet valve. Now let's implement a proportional controller to control the water level of a tank in factory I/O. As I showed you at the beginning of this video, we generated this program and also we tested it. Notice that in a proportional controller, the error value is multiplied by a constant number Kp to produce the controller's output. So we can easily use math functions to compute the output of the proportional controller. Since the proportional controller is categorized as a form of PID controller, therefore I would like to go ahead and use a PID function to implement the proportional controller. First, let me to deactivate the second function, which is the on-off controller of the inlet valve. Because the result of this logic will be false forever, PLC won't execute the second function FC2, or you can delete the whole network from the program. To implement a PID controller, we can go to a standard library, to PID control blocks, and select a suitable function. As you can see, we have 5 function blocks to implement PID controllers. To implement a continuous PID, I need to select FB41 cont C IC cont function block. Let's take a look at the definition of the FB41 function block on the SIMATIC Manager software help section. The main point in using the PID function blocks is that you cannot use them in the main block OB1. We can use them only in one of OBs, OB30 to OB38, which are executed cyclically with fixed period time. As an example, let me add OB33 to my project. Okay, I added OB33 to the project. If you look for OB33 in the help section of the software, you will see that the default interval and priority class of OB33 is 500 milliseconds and 10 respectively. Inside this table, you can see the default interval and priority class of the other OBs. Now let me open OB33 and enter a PID function block inside of it. Note that in the previous videos you got familiarized with functions FC, but a PID controller program is written inside of a function block or FB. The difference between the function blocks abbreviated as FB with the functions abbreviated as FC is that the function blocks need a data block that are abbreviated and defined as DB to store data and parameters. As you can see, after defining DB1, it is added to my project. Note that until now I have added 3 new blocks to my project: OB33, which is executed every half a second, and FB41 or PID function block is entered inside of OB33, which it uses DB1 to store its necessary data and parameters. Note that if I decide to use FB41 function block to add a second PID controller to my project, I will need to add and define a second DB such as DB2. As you can see, FB41 has lots of inputs and outputs. Now let's go ahead and learn how we can use the FB41 function using the help window. As you can see, after some details related to the controller's setting, a diagram shows the controller's performance, and finally, at the bottom of the window, we can see more details about the inputs and outputs of the controller inside 2 tables. Naturally, in order to use a PID controller, we need to determine desired and real values of our industrial parameter. In this video, our industrial parameter is the level of water inside the water tank system. Notice, based on the PV per on parameter, only one of these 2 inputs will be used. The first one, PV in, is a real number like the SPINT input. The PV in determines the current value of our industrial parameter. Its value is used directly by the PID controller without any changing. But if PV per on parameter is set to 1, the PV per will be used. The scale of this input can be changed by the parameters of these 2 blocks. Usually, this input is connected to an address of analog input modules to read an industrial parameter directly and then change its scale. Note that by default the PV in is selected. Note that I wrote a program to determine my desired and current level. Now I only need to use these 2 parameters which define the PV and SP values of the water level in the tank. Now, after feeding these two signals to the controller, the difference of these two signals is equal to the error value. Notice that the error value is connected to deadband section, which its default preset value is 0, but we can set it to a different number. Gain is the next parameter, which is the same as KP coefficient that I already explained about it. As I mentioned already, the PID algorithm consists of three basic coefficients: proportional, integral, and derivative. By default, the proportional and integral terms are activated. Now let me set the I cell to 0 to deactivate the integral term. Also, let's define gain value. So based on my settings, my PID function block will be used as a simple proportional controller. Notice that I can enable or disable each term of my PID controller. Right now, only the proportional output is activated. The controller's output can be added with the DISV parameter. By default, its value is equal to 0. Now I should determine that I want to control the inlet valve using the produce controlling signal or manually. For example, I can connect the man input to a potentiometer to control the inlet valve manually. Remember, my current program already included a program to control the inlet valve manually with a potentiometer. But I want to control the inlet valve by using my proportional controller's output. Note that by default, the manual mode is selected. My program should execute my PID function block only when the automatic mode is selected. Also, I need to use the man on parameter to disable the manual mode of my PID function block. In other words, enable the automatic mode. Now I am going to define LMN parameters on my controller block to limit the output of my proportional controller. Let's define 0 and 100 as mean and max values of the produced signal respectively. Now, after setting the LMN values on the controller block, I can also alter the range of the output signal by LMN norm section and use the output result signal as the LMN output. Because I defined the range of signal between 0 to 100, the output of CRP out or LMN pair is going to be a number between 0 to 27648. So if I connect LMN pair parameter to one analog address of an analog output module based on its settings, an analog signal of 0 to 10 or 4 to 20 milliamp or so on will be generated to control the inlet valve. Notice that the help window explains how these two blocks, LMN norm and CRP out, can be used. Since I already defined the mean and max values, I will have a number between 0 to 27,648 on the LMN pair output. So I only need to connect LMN pair output to the address of my analog module, which is connected to the inlet valve to produce a voltage between 0 to 10 volts to control the inlet valve. Okay, my program to control the water level of the tank using proportional algorithm is ready. As it was mentioned already, I used DB1 to store all data and parameters related to FB41 function block. And if I open DB1, I will see the whole of the information that is stored inside DB1. As an example, in this column and these rows, you can view the preset values related to gain, TI, and TD coefficients. Remember that the control program that is created so far is a proportional controller, and its derivative and integration terms are not active. Now let's download the new program into my virtual PLC. Notice in the previous videos I showed you how to create a connection between a virtual PLC and factory I/O. I am going to use the virtual PLC to control the water level of the tank. Alright, let's activate the auto mode of the controller while the outlet valve is closed to see how the controller performs to bring the current level of the water from 35 to my desired level, which is equal to 150 centimeters. As you can see, as the water level approaches the desired level, in other words, when the error value decreases, the inlet valve starts to close. Now let me to increase the desired water level to check the performance of the controller better. As you can see, the proportional controller can bring the water level to the desired level precisely without producing any fluctuation on the water level. The weakness of this controller is revealed when I open the outlet valve. Let's see if the controller can bring the water level to the desired level precisely as it did before or not. I opened the outlet valve a little. As you can see, as I opened the outlet valve, the controller tried to bring the current water level to the desired level. As you can see, the desired level is equal to 210, but the current level is 182. So there is a difference between my desired level and the water level. In other words, the final error is not equal to 0. Now let me open the outlet valve more to notice the weakness of my proportional controller better. Now I decrease my desired water level to 40. As you can see, the output of my controller is 0. In consequence, my PLC closed the inlet valve. Now while the outlet valve is open, let me raise the desired water level again to check out the performance of my proportional controller again. As you can see, there is an error between my desired level and the current level. That means proportional controller cannot control the water level precisely as long as the outlet valve is open. The reason is obvious. When the outlet valve is open, the controller needs to open the inlet valve to prevent the water level from dropping. But as it was mentioned earlier, the controller output is computed by multiplying the error value by the Kp coefficient. So the error should not be zero to have a non-zero signal at the output of my proportional controller. In this condition, the proportional controller can open the inlet valve. Alright, we investigated the performance of the proportional term. As you can see, we can add the integral and derivative terms to the controller in a parallel form. Let's check the performance of the controller when it is only using the proportional and integral terms. As in case of the water tank, let's assume that set point value is 110 centimeters and the current water level or PV is equal to 90 centimeters. Naturally, the error value E0 is 20 centimeters. As you can see, the output of my PI controller consists of only two sections. In the beginning, because elapsed time is small, the output of the integral section is close to zero and the output of the proportional section is not zero. So the proportional section plays the main role to determine the output of the controller. A non-zero number causes the controller to open the inlet valve. For example, let's assume the PV value has reached 100 centimeters and therefore the E1 is equal to 10. Notice that as the error value decreases, or 10 versus 20, the output of the proportional section is also decreased, but with the passage of the time, the output of the integral section will no longer be equal to zero. Up until now, the error values are positive, so the output of the two terms is positive. In consequence, the inlet valve will be open to raise the water level and to decrease the error value until the error value to reach 0. Notice that when E3 is equal to 0, the output of the P term is equal to 0, but the output of the integral part is not equal to 0 anymore. We saw an example that sometimes in order to keep the error value equal to 0, the output of the controller should be a non-zero number. Now, the integral term can use the previous errors to compute a non-zero output value. This feature can help to keep the water level at desired SP value, but it has a weakness in the beginning. Now, the previous error values are larger numbers, and when the integral term sums them to determine its output, it will generate a large output value to open the inlet valve as well. So it causes the PV value to pass from the SP value. For example, the PV value can reach 112 centimeters, which is greater than the SP value. But when the errors are negative, the controller tries to close the inlet valve to decrease the water level and return the PV value to the SP value, which is equal to 110 centimeters. Let's assume that this black line is the indicator of the desired water level and the red curve is the indicator of the water level inside the tank. Notice that by adding the integral term to the proportional controller, it takes a longer time to bring the water level to the desired level, but on the other side, it can bring the water level to the SP value and keep it at the SP level with a very minor error. Pay attention that at the beginning of the controlling process and when the error values are high and the elapsed time is small, the proportional section plays the main role to determine the output of the controller. But with the passage of time and the reduction of error values, the output of the integrator term plays the main role to determine the output of the PI controller. Also, pay attention that although the integrator part of the PI controller is able to reduce the weakness of the P controller, which was investigated, but it introduces a new problem to the performance of the PI controller, and that is the presence of fluctuation at the beginning of the red curve, and as a result it takes more time for the water level to reach the desired level. In general, in some applications, the weakness of the integrator part can be ignored, but if we want to minimize the presence of these fluctuations, we can add the derivative term to the controller. Try to describe the function of the derivative part of the PID controller for yourself, just like my explanation for the integral part. Pay attention, depending on the system's conditions and requirements, we can increase or decrease the effect of each section of a PID controller by changing the related coefficient. In this diagram, you can generally see the effect of each coefficient of PID controllers to bring a process value to its desired setpoint value. Alright, let's check the performance of our PI controller using the water tank system. Remember, we disabled the integral term of the function block 41, but in this video we need it. So let's remove this input. Note that the performance of a PID controller can also be defined by this mathematical formula, and according to that, I set a time of 5 seconds for the TI coefficient related to the integral part. Now let's connect an address from the memory to the ER output to see the error value. Now let's download the designed PI controller to control the water level. Well, here is a problem. My PI controller performs like the proportional controller as we observed. I checked my program and I found the reason for my problem. Note that when the FB41 is used for the first time, by default its integral term is enabled. But I used my FB41 and I disabled its integral part, and now I need to activate it by setting it to 1. Also, I prefer to change gain and TI coefficient to 2 and 10 seconds respectively. Okay, my PI controller has started its work. Pay attention that the outlet valve of the tank is permanently open and the controller only controls the inlet valve. As you can see, by using the integral term, my PI controller can raise the water level to the desired level and keep it at the level with a very small error. Again, let's change the desired water level to observe how the PI controller performs. If you pay attention to the changes in the water level or the sign of error values, you will notice that before the water level is fixed at a desired level, it goes up and down around the desired level, and then it stabilizes at the desired level. As I explained earlier, the reason for these fluctuations is the use of integral term of the PI controller. Again, let's change the desired water level. As you can see, the performance of the PI controller to control the water level is satisfactory. We can use this PI controller in many industrial applications. But if we need to have a faster controller, according to the video, we can add the derivative section to the controller. To activate the derivative section, we need to activate the diesel parameter and assign a value for the TD coefficient. Now let's change the desired water level and test the performance of the PID controller. As you can see, the PID controller can raise the water level to the desired level and keep it at the desired level with a very small error. Thanks for watching this video. See you in the next one.